Imagine driving a robot from any browser. No app, no remote, just Wi-Fi. In this project, your ESP32 becomes both the robot controller and a web server, so you can send movement and speed commands while testing range, response, and safe stopping. You've already built the foundations: sensing with LEDs, buzzers, light, ultrasonic, and weather sensors, movement with motors, gates, line followers, Bluetooth cars, and obstacle avoidance, and Wi-Fi connections between devices. Now those skills come together in an ESP32 robot that moves, communicates, and responds to commands from a web dashboard. The mission is simple. Turn the ESP32 into the robot's brain and its web server. Instead of using a special app, any browser becomes the controller. Tap forward, left, stop, or change speed, and Wi-Fi carries that command to the robot. Think of the robot as a chain of responsibilities. Your phone or laptop is only the user interface. When you press a browser button, that action becomes a web request sent over Wi-Fi to the ESP32. The ESP32 reads the request, matches it to a movement command, and sends control signals to the motor driver. The motor driver handles the higher current needed by the DC motors, and the chassis moves forward, backward, left, or right based on motor direction and speed. Before coding, make sure each hardware part has the right job. The ESP32 is the brain, but it should not drive the motors directly. It sends small control signals to the motor driver, and the driver uses battery power to deliver the higher current the motors need. Plan power carefully. Weak batteries, shared overload, or missing grounds can cause resets and unpredictable movement. The key wiring habit is a common ground between the ESP32 and motor driver, so both devices interpret signals the same way. The ESP32 has two common Wi-Fi roles. In station mode, it joins an existing router or phone hotspot, just like a laptop does. This is usually best indoors, where devices share the same network and range may be better. In access point mode, the ESP32 creates its own network, and your phone or laptop connects directly to it. That helps when no router is available, but range and internet access may be limited. Either way, you open the robot control page by entering the ESP32's IP address. Picture the ESP32 as a tiny website running on the robot. It creates or stores a small HTML page with buttons like forward, left, right, and stop. When you type the ESP32's IP address into a browser, the browser asks for that page, and the ESP32 sends it back. Then pressing a button sends a simple command to the ESP32. The code reads the command and translates it into motor actions, so the robot moves without a separate app. As you design the web controller, think like the driver. The most common actions need big, obvious buttons: forward, backward, left, right, and stop. Speed can use slow, medium, and fast buttons, or a slider for finer control. Give stop special attention. Make it large, red, and easy to hit quickly. Since many drivers use phones or tablets, every button should be touch-friendly, with enough space to avoid accidental taps. A browser button does not drive the motors directly. It sends a short web request to the ESP32, such as /forward or /stop. The ESP32 reads the request path and chooses the matching function: move forward, turn left, stop motors, or set speed. A speed request can also include a value, like 150, so the robot knows how fast to move. Simple command names make the program easier to test, read, and debug when something behaves unexpectedly. Each request is a tiny message. For movement, the ESP32 acts as the decision maker, not the power source. It sends two kinds of signals to the motor driver: direction and speed. The driver supplies the actual motor power. Forward usually means both wheels rotate forward together. Backward reverses both. To turn, the robot creates a difference between the left and right wheels. One side may slow down, stop, or reverse while the other keeps moving. A stop command should cut motor output immediately, so the robot responds predictably and safely. Speed control does not require the ESP32 to send true analog half power. Instead, it uses PWM, very fast on-off pulses. When the pulses are on for only a short part of each cycle, the motor receives less average power, so the robot crawls. When the on time is longer, the motor gets more average power and moves faster. That is how slow, medium, and fast buttons can map to preset PWM values. Smooth speed control makes steering easier, especially near obstacles. Build in small testable steps. Start by connecting the hardware and checking power, ground, and motor driver wiring before any code runs. A wrong wire here can damage the board or driver. Next, upload a simple motor test sketch and confirm each motor spins in the expected direction before adding Wi-Fi. Then add the web server code and use the serial monitor to find the robot's IP address. Finally, open the web page and test forward, back, left, and right one at a time. If something fails, stop and fix that stage before moving on. After the robot responds to remote commands, test how well it responds. Change one variable at a time, starting close, and then increasing distance in measured steps. For each trial, record whether the command worked, how long the delay felt or measured, and any signal issues you noticed. This turns vague comments like "it was slow" into usable evidence. Response time shows speed, range shows limits, and reliability shows consistency. If a test fails, retry and compare results before deciding what needs improvement. Treat stopping as the robot's most important feature, not an extra. Make the stop control obvious and test it repeatedly while the robot is moving. Then add a failsafe. If the robot does not receive a command for a short time, it should automatically stop the motors. Always test on the floor in open space before going near people, walls, or furniture. If behavior seems wrong, check the basics first: IP address, battery level, motor wire direction, and Wi-Fi delay. You've now moved from basic movement to connected robotics. The ESP32 can host a web page, receive button commands, and turn them into motor actions, speed changes, and safe stops. Testing range and response time shows how real IoT systems behave. Next, you'll apply these same ideas to plant care, security alerts, and stronger debugging.